So, and I want to remind people too that we are getting pretty much a AP classroom assignment almost every day. I've got a few people that I don't have any scores for, but I think there may be in some cases, there's some issue with AP classroom because I talked to Aiden today and he said he's done them all, but they didn't show up. And I had another student, Zach, in AP Calc who said his won't open up. So I don't know if that's like a Chromebook issue or if that's an AP classroom website thing or whatever. So yeah, I posted those on PowerSchool. Take a look at your grade on those. If that doesn't match what you think you've done, let me know, because it may be somehow in, I don't know what, it's the mysteries of the technology that my score, what I've seen, may not match what you are doing and what you've seen, and we can try to resolve that. So I don't know what that issue is.
So is our scores on PowerSchool scores we got on the test, or is this still like a booster grade?
Scores you got on the test, or what was the
For
other
the
option?
AP classroom tests?
No, so, no. The scores you get on the AP classroom are not, I'm not taking those for grade at all.
Okay. Good.
That's just feedback, that's just feedback for you.
Okay.
And they're gonna be low, because those are hard questions.
Mm-hmm.
I'm grading them on completion.
Okay.
So every AP classroom assignment counts as 2 points. So, and I'm trying to enter them in kind of batches of 4. So, like 1 through 4 will go on there as a score out of 8. So if you did them, you got both the points. But if you didn't do them, or at least if it doesn't show on my end that you did them, then I'm entering that as a 0.
Okay.
So if you get you'll see a couple of scores on there, I think. If you got 8 out of 8, that shows that I see them all. A 6 out of 8 means that I didn't see that you did one of them. And if you don't think that's accurate, let me know and we'll try to resolve it. But do check it, because I think there may be some issues in some cases, and I don't know what that's about. Okay. Questions on homework? Oh, and let me back up too, because I want to say this for people at home too. So the gateway exam is like before, that it's a test just on derivatives. So there's 12 of them on there. So they're each worth like, I don't know, 8 points or something like that. There will be a little bit of partial credit, but not much. So basically, if you can do the derivative correctly, you're going to get almost all the points. If you make a mistake on the arithmetic cleanup, then you might lose a point. But if you don't do the derivative right, there's not much partial credit. Then you're kind of losing those points. You must get an 80% or it's a 0. And if you don't get if you get a 0, then you just have to come in and retake it until you do get 80%, at which time that 0 will be replaced by an 80.
So could you pass the exam with an 80% by just doing the derivative and none of the cleanup?
That would be a risky strategy.
Hypothetically.
I'm not even going to answer that. So, and I'm asking you to do it on your own time. I debated how to do this in past years. I would just give the gateway on a day where we had 90 minutes, because the gateway itself isn't really that long. You're doing 12 derivatives. So I don't know, what did it take you, Grace? Maybe 30 minutes or? What's that?
I think so.
About 30 minutes. And I think Grace checked every one about 19 times. So it's not a long test. So I didn't really want to make you come in on a Friday morning, although you're welcome to do that if you want to do it then, if that works out better for you. Or you can come in on your virtual day and take it then, or you can come in after school. So I just kind of left it open. I didn't want to take, because I only get to see you in person twice a week, I didn't want to take a big chunk of that time just to give a test. So this time I kind of feel is pretty precious, and I try to kind of guard it a little bit. So go ahead.
Would you just want us to come in during like your planning periods then?
Yeah, so you can either come in like at 9 o'clock on a virtual day for you, or you can come in after school any day, or you can come in on a Friday morning. Any of those is okay with me. So I just didn't know what's convenient for you, whatever works for you. Okay? Anything else? All right, well, because of my screw up last week, I'm trying to trying to fix that. So we're going to talk about connecting f prime and f double prime to the graph of that. So this is back to 4.3. And this has to do with homogen of 38. So we'll hopefully be back to where we're supposed to be and try to, as much as we can, progress in a sequential manner. So we're going to connect f prime and f double prime to the graph of that. So one thing that we notice is if we know the graph of f, I'm going to put down a crazy looking f here, and say we have something like something that starts out looking like a polynomial, and then we'll throw in some other interesting parts to it. Maybe something. Come down like cusp. I think we're approaching some asymptote. So here's f. Yeah, you're welcome. So things we need to know. If this was a polynomial, which clearly it is not, then we would think that f prime would be 1 degree less. So if we had something that looked like a 4th degree, we'd expect the derivative to look like a 3rd degree. We can see where, there's horizontal tangents. And horizontal tangents in the function are x-intercepts in the derivative. So those aren't known values there. We can see where there are, for example, inflection points. So where this thing, we can see that the slope of the tangent line goes from 0 to smaller negatives to bigger and bigger negatives. Somewhere in here there's an inflection point, and that's the steepest negative slope of a tangent line we're going to see, which means that a place on the original function where there's an inflection point will correspond to like a relative minimum or relative maximum in the graph of the derivative. Is that okay? And so we have something like that. So here, we can see that it's approaching 0, but maybe just a little bit positive. And so it's going to, and I think there's maybe an inflection point somewhere in here. So I'm going to call that a relative maximum. So it's going to do this. It's going to come down here. It's going to hit here. And it's going to come there. And I don't know, it's going to be positive up here. And then when we get to this place here, so that's a corner point. So that means it's going to be undefined in the derivative. So I'm graphing y equals f prime here. So that means there's going to be a blank spot in the derivative. And so then we try to read, it looks like this was a bigger positive number than here. So as we transition from this piece here to this piece here, the derivative is going to drop down, something like that. And a straight line has a slope that is just the slope, and that's positive. So it's going to be a horizontal line at whatever that slope is. And I didn't put any scaling in there, so I don't really know what that slope of that line is. But it's definitely positive, so it's going to be up above the x-axis. You okay with that? And another corner point is going to be undefined. Now we have a straight line segment that's got negative slope, so we're going to jump down, and I don't know what that is. I'm going to say there's that slope of that line. That's the negative slope of that line. We have another corner point there, so another little blank spot, a little open circle. And now what I'm trying to show here is to look like a vertical tangent. And so our slope here looks like it's about 0, so I'm going to jump there. And it's going to get positive, and it's going to get bigger and bigger and bigger until it goes off the charts to positive infinity on this side. So that vertical tangent is going to be a vertical asymptote in the derivative. Okay? And when we hop over to the other side of the vertical tangent, that's still a really big positive. So it's going to go to positive infinity, the same infinity on both sides of the vertical asymptote. Then it's going to drop down until we get to 0 here. So there's going to be another horizontal tangent there. And we can do something like that. Okay, so far? Then it's going to go to, now we have negative slope, a little bit at first, bigger, bigger, bigger. Now this is supposed to be a cusp. So it's going to go, fall off the table, go to negative infinity. So we have another vertical asymptote at the cusp, like we did at the vertical tangent. So this is going to drop and go to negative infinity. Different than the vertical tangent, once we hop over to the other side, now it's a really, really big positive slope. So it's going to go to, it's going to be a vertical asymptote at the cusp, but different infinities on either side. And then it's going to level off and approach this asymptote. So it's going to approach 0, but always be a little bit above the x-axis. Okey-doke. Okay. So, can I destroy the evidence here? Okay. So our first derivative test for relative extrema. So at least for interior points, so for interior points, we'll talk about the endpoints separately. So if you have some function, and then how do we start? Take the derivative, find the critical, so set it equal to 0 and solve. Okay, so we're going to find, I'm going to say, am I okay abbreviating CPs? Those are critical points. And then I'm going to put in parentheses. What we mean by critical points are where the derivative is equal to 0 or f prime of x is undefined. So remember, both of those qualify as critical points, which means the derivative may change sign at that place. Okay, but you have to check it. Is that okay? So if, then if, I should say for interior points, let me back up, of a continuous function f. So we're assuming now that the function is defined at this point, because we can't have a relative minimum or relative maximum like at an asymptote or something like that. So the function has to be defined there. It may or may not be differential. We could have a cusp or a vertical tangent or some kind of corner point that could still be a relative min or relative max, but not like at an asymptote or some kind of discontinuity there. So if f prime of x changes from positive to negative, then we say, and remember, just to remind you, in the world of AP, a relative min or relative max must be given as an ordered pair. So then I'm going to say C comma f of C is a relative, and it's also referred to as a local. So relative and local are interchangeable, maximum. Okay, remember that? And likewise, I'm not going to be as, say as much, but if f prime, so if f prime changes from negative to positive, then C comma f of C is a relative min. Now, it doesn't have to do that. I mean, it may not change sign, so it could go positive, positive, or negative, negative, in which case it is not a relative minimum, nor is it a relative maximum. So if the first derivative was 0, and that's why we got the critical point, and it goes positive, positive, or negative, negative, we call it a shelf point. But if it came from some other kind of discontinuity, we could have a corner point where it's increasing and the derivative is undefined, like in a piecewise function, then it goes back to increasing. So it's not a relative min, it's not a relative max, but it's not considered a shelf point if that critical point came from where the derivative is undefined rather than where it's 0. Okay, now some books don't, it just depends on the author of the textbook. So some authors don't consider endpoints to be a relative min or a relative max. They say relative mins and relative maxes can only occur on the interior. Other authors of other textbooks think that they can be a relative min or relative max. Our author falls into that category. So in our textbook, they are going to ask you to consider the endpoints as possible relative mins and relative maxes. So in that case, you can't really say that the derivative changes sign because it's not even existing on the other side. So you just have to use the appropriate sign. So, as long as this is continuous, so we know this, then if the derivative, so for a left endpoint, if f prime is greater than 0, then that's going to be a relative min. You kind of have to just look at it there. And if the f prime was negative, if the function decreased coming away from that left endpoint, then that would qualify as a relative maximum. And similarly on this side. You just kind of have to think your way through it. But in our textbook, if you're checking your answers in the back, then they're going to look for relative mins and relative maxes at the endpoints as well. They'll never come up on the AP exam because they're not going to try to make you, you're not going to choose one author as correct, of a textbook as correct and the other not. So it'll never come up there. Concavity, we know, comes from the second derivative. So we should maybe get a definition first. So we understand concavity. So the graph of a differentiable function, graph of a differentiable function, function f is, and then we'll say part A, it's going to be concave up. And there's different authors define this differently too. So, but they're consistent with what their end result is. So our author says that a function is concave up, and then they say specifically on an open interval. So there is no question that we are only talking about open intervals for concavity. So increasing, decreasing, you will include the endpoint if the function is defined there. So it can't be increasing on a closed interval if there's like a vertical asymptote or something. But always open intervals for concavity. If we will say f prime is increasing on that interval. So, and I'm going to throw out another interpretation of this too, because there are places where it comes up, and sometimes even on AP exam questions where knowing the other kind of understanding of concavity can be useful. So we can see that, if a function is concave up, is bowl-shaped up. And you can see that the slope of the tangent line here would be negative, and as you go from left to right, it eventually becomes 0, and as you keep going from left to right, then it becomes positive. And so certainly going from a derivative, the slope of the tangent line, which is a derivative that goes negative, 0, positive, it's increasing, the derivative is increasing as you make your way from left to right. Now, another way of thinking of it is some books, some authors describe a function is concave up if the graph lies above all of its asymptotes on that interval. So that's another kind of interesting and neat way of thinking of it, is that concave up means it lies above its tangent lines. And then similarly, you can get the concave down. I'm not going to be write it out in as much detail because it just changes the appropriate things on an open interval if f prime is decreasing on that interval. And likewise, you can see that the graph of a function that is concave down, you can first of all see that the slopes of the tangent lines, which is the derivative, is decreasing because they're going from positive to 0 to negative as you go left to right. But you can see that for a function that is concave down, on the interval that is concave down, the curve, the graph, will lie below all of its tangent lines, which is a sometimes useful way of thinking of it. And of course, we use our test is to use the second derivative. So we test for concavity because we said it is concave up, then the slopes of those tangent lines are increasing, and the slopes of the tangent lines are given by the first derivative. If the first derivative is increasing, that means the second derivative is positive. So we'll say if f double prime of x is positive, that means the original function is going to be concave up. And if the second derivative then is negative, that's going to mean that the original function is concave down. So our test for concavity is the second derivative, although, you know how AP is, they'll sometimes find a roundabout way to get to it. It would be correct to say that, you know, this is concave up because its first derivative is increasing. That would be a legitimate justification for being concave up, if somehow we knew that the derivative was increasing on an interval. All right. Question? So let's see. I've got an example here. We can do this. Let's see. So if we have f of x is equal to x cubed minus 12x minus 5, shall we find intervals where f is increasing and decreasing? Let's find any relative extrema. Let's find intervals where f is concave down and concave up, and find any inflection points. Okay, let's do that. I think it's time for Kent to probably come to the board, don't you think?
It is. I was thinking that same thing.
Links are getting way too long.
That's plus 2x minus 2, right?
Yeah, 2 would make more sense.
Good. You'll need. So I think we're reaching consensus as we do here on where the function is increasing. Notice increasing, decreasing, you're including endpoints. Your justification is because the derivative changes from positive to negative or negative to positive. And you have to give your relative mins and relative maxes as ordered pairs. The intervals where it's concave up and concave down are open intervals. And on the inflection point, your justification can be just that the second derivative changes sign. Doesn't matter if it goes positive, negative, negative, positive. I'm going to run out of time before I talk about the second derivative test for relative mins and maxes. Remember, the way that goes is you find the critical points, which are where the derivative is 0. The derivative being undefined isn't going to be useful with the second derivative test because if the first derivative isn't defined, neither is the second derivative. And you're going to take that critical point that made the first derivative 0, plug it into the second derivative. The second derivative is positive. That means the function is concave up, where it has a horizontal tangent, and that's going to make it the relative minimum. If the second derivative is negative, that's going to make it the relative maximum. And if the second derivative is 0, then we don't know, you're going to have to do something else to resolve it. But it just won't work for that. It's on the video if you need to check it out.